All right, hello and welcome to GLOBEBUSTERS, Season 14, Episode 9. Today we're going to be doing a review of Cosmological Redshift. We're going to be breaking it down to its very components and then seeing what the lads have constructed with us for us to believe in and what they've backed it up with physics and field equations that only a few men in the whole entire world have ever answered. But before we do that, we're going to get a word from our panel. Shane G, how are you, sir?
What's up, everyone? Good to be back again. This is going to be a good one.
Stone G, how are you, sir?
Kicking ass, taking numbers, and wow, what a week it has been. I will say that little.
I heard there's been a lot of going nowhere fast.
Well, yeah, there's been a lot of circle jerking for the past week. Lots more Shiva changing up the game. We had a Globey Idiot review last Sunday's broadcast. Rather conspicuous timing, I must say, given what else is going on in the Twitterverse these days. That's all I will say about that at this point as well.
Nice.
Yeah.
Nice. Well, maybe we'll get a little recap at the end of that to touch base and see what's going on in the Twitter sphere. Or the Twitter plane, as they call it.
The
Twitter hemisphere of dome vision. I don't know. We'll figure it out, guys. It's not a real sphere. It's all good. All right. So let's see here. We'll get into the presentation. I'll do a little screen share here, and we should get a nice, clean infinity screen. Very nice. And we should have the presentation over here.
Oh, is that Halton right there? Cool. What a man, what a man, what a man.
It's our boy. Yeah, I just need to change this to... No. Change to GLOBEBUSTERS. And then... One second, need to fix the cropping here. And then 400. All right, there we go. All right, just a second, lads.
There's no evidence of this, but this error is definitely caused by Linux.
No, what? How dare you? That's not true. That's not that true. All right, there we go. We're back, boys. Sorry about that. We're all properly cropped up on the screen. Everyone can be seen. All right, we'll go ahead and get into it. Just got to get my notes here. All right, so we have here Holden Arp, who made some interesting observations with a telescope, and his interpretation of what he saw completely contradicts the mainstream narrative of how they present distances and velocities to us in regards to objects in the area that they call space. So primarily, we're going to be looking at galaxies and quasars. So we'll go over some definitions and stuff and some basics to get an introduction into what they're measuring here and how they're presenting it to the public. But yeah, as we go through here, Holden Arp was a PhD graduate from California Institute of Technology. He worked as the main astronomer at Mount Wilson for 28 years. He was in charge of a lot of big projects, tons of accolades in the astronomical community, and he has probably 50 or 60 galaxies and stellar objects named after him. So this dude is a major player in the scene of astronomy, and what the conclusions that he was drawing were not liked by the mainstream. And we'll get into all of what those are and what the implications are. But we're going to cover primarily from his book called Seeing Red, and this was published in 2002, where he was finally had enough of being censored and ignored about these observations, and to the point where his career was tarnished, where he was no longer allowed to use observatories in America. He had to go overseas and basically get hand-me-out jobs to work in the observatories so that he could use the telescopes to keep making observations. The man truly loved his job, and he was just reporting on what he saw and trying to make sense of it in the mainstream cosmology, essentially, without going too far into contradicting it. But just as far as he went was too far. And because of his accolades, he definitely had the weight to challenge, the official narrative. So if all these people don't agree, then there's no unified narrative that can be drawn. So they all have to kind of toe the line. So when this guy showed up and was like, "Hey, I got a bunch of observations here that completely contradict everything you're saying," well, this is how they had to handle him. Just ignore and censor. So why are redshifts the key to extragalactic astronomy? Now, what is extragalactic astronomy? That is the field of astronomy that deals with things that are far outside of what's considered to be the distances for our solar system and whatnot. So this is the study of galaxies, how galaxies are made, how stars are made, that kind of stuff. So they get into these extreme distances, and perceived distances, really, because they don't have any idea. But layer wise, they're on the cutting edge of the horizon of the universe, so to speak. Whereas everyone else is doing things like either in the solar system or some intermediate range there. But anyway, we'll read a couple of important quotes here to kind of set the baseline for why redshift is so important for cosmology, and why it's and how it serves as the backbone for all the ways that they try to interpret what they're looking at. So redshifts. We look at the light from an object after it has spread out from short to long wavelengths. We see peaks and valleys due to the emission and absorption from the atomic elements. One thing we can measure is how these features are displaced from the wavelengths in a standard laboratory. So obviously, going into space is a huge hurdle, but we have measurements in the lab using light and different elements. So you can burn gas and do spectroscopy and look at what the emission spectrum, and we'll get into the emission spectrum and absorption stuff here as we continue. But basically, they have all these values and frequencies categorized here on Earth, and what else can we do with those? Well, when they look up and split starlight, they analyze those frequencies and they compare those to the terrestrial lab measurements, and they're like, oh, well, there's differences here. These wavelengths are longer and or shorter, which constitutes as redshift or blue shift respectively. And from that, they start to draw conclusions, because in the lab, like on Earth, Doppler shift is a real phenomenon that shows proportionality to velocity, and so from that interpretation of the wavelength shift, they attribute everything that comes in the sky or comes from us from the sky as it's being shifted in red, and that's due to the expansion of the universe itself. So we're going to look at how we got there to understand that the universe is actually truly expanding out from us. This is the only tenable position that they could come up with after making all these observations, because there's no real mutually exclusive observation that they've made. Like, no one's ever looked in the sky and went, "Oh, dude, this can't be explained for geocentrism." It's definitely this cosmology. Everything they see says the opposite, and they have to come up with different interesting ways to say, like, oh, well, it just looks that way because of all the motion. So one of the ways that they do that is through this mechanism of expanding the universe. And they do that based off of Edwin Hubble's measurements from the 1920s and what he was putting forward. They've made some tweaks and refinements to that, but all of this is based on, it starts with a ladder. And in every rung of the ladder, they say gets, it's built on the previous, which tells them the known distances. So we're going to look at how they came up with the original way to determine distances and all that. But before we get into the specifics of it, this is more just an overview. We're going to look at some of the pictures that ARP took, and then we're going to look at some confirmations of what ARP categorized and put out there. Some amateur astronomers have taken similar pictures of what he was putting forward. So this is really important because in the time of the James Webb Telescope, we're getting all this new information, right? We're getting things that are contradicting the Big Bang model. They're contradicting relativity theory, and we don't even know. Like nobody's ever seen these things, so like we can't confirm them. Like the wavelength and the distances and sensitivity that they're working with, that they say out there, gives them, all this unique insights into these things, and that's what's allowing them to see quote unquote further. So none of us can confirm any of this stuff. So the furthest that I'll take any of this so far is observations where amateur astronomers have confirmed it. So everything that ARP has put forward in terms of all these galaxies and nebulas and all these different classifications that he's got, at least other human beings have seen them with their oculars. So that's pretty good positive.
I must say, though, that these frames that you're just showing now, they're much prettier than the crappy PDF black and whites that we were looking at when we were reading through his PDFs on our Tuesday night reading sessions. These are nice. Congrats, man.
Dude, I found some sweet ones, but he totally tricked us because he gave us all the black and white ones throughout the book, and then the good ones are in the back. He has them all labeled in the back.
Gotcha.
So yeah, we'll take a couple look here. We'll take a couple shots of just some random ones just to see what kind of stuff they're doing. Now, most of these are in false color. So false color is just the artist rendition applying arbitrary color values to different wavelengths, and then that allows you to see basically the visible spectrum without having it oversaturated with the primary light that was coming through there. So when we see things in true color, we'll go over the distinction there between that. But this is kind of dim, so you can kind of see all the effects there instead of just a primary one. So these are just different stellar objects out there with coordinates that anyone can look up and see for themselves. So here are there was about 10 people on the list that have websites posting their confirmations of what ARP was putting forward. I chose 2 randomly and just went through about 5 or 6 of them. So these are we can compare and contrast on what was being put forward here. So these are, and not all of these are the same ones, but yeah, these are confirmed by the people. So these are different images here, different telescopes that were used. We'll just breeze through these here. The text is just what the person wrote down when they made the observation. So it just gives descriptions of things, coordinates, etc. None of it's particularly relevant for what I'm going to be putting forward, but I figured I would include it anyway, so there would be nice stuff on the screen. All right, more objects, more galaxies, more quasars. Quick note on galaxies. So galaxies are broken up into various classification. There's tons of them. We'll go over a couple as we go through this. But the important thing to note about quasars, what is a quasar? Quasar is a point source of light in the sky that's essentially stationary, and it emits a ton of X-ray and gamma radiation.
The word itself, just for background, is a condensation of the term quasi-stellar object.
Yes. Yeah, it's just a term they made up. They have no idea what these are or how they function or exist. There's many hypotheses on what's at the center of a quasar. Is it a black hole? Is it shooting out energy from that black hole? Is it a massively dense object? They have no idea. All they know is that there's a dot in the sky that's just emitting tons of energy from it, and usually they're really redshifted. So they interpret this as, okay, that must mean that they're really far away and that they existed before the galaxy existed. So some of them say that, these are early star/galaxy formations, etc. They have a completely backwards timeline and evolution as per the Big Bang Theory and using redshift as a recessional velocity to place the distance to these objects. So they've got a real strict framework of interpretation to place these. And what ARP noticed was that when you look at these objects in different frequencies of light, different spectrums, you'll see that sometimes they're connected by a luminous filament, and sometimes they're connected by an actual filament of of gas or whatever material is in between the galaxy and the quasar. And so mainstream has to come up with ways to explain, like, well, it's actually behind the jet stream. It just looks like that. But when we're looking at these images, there's no depth to them. You can't tell one's further than the other. This is all interpretation based off of splitting light and looking at the spectrum and then applying absolute velocities to them. But then saying that that's not the absolute velocity. It's just the velocity. It's the relative expansion of the universe in between those two. So they get a little, they give themselves a little wiggle room with their velocity situation there. So there's all the galaxies and dots in the sky. And as we'll see here, there's some quasars in this galaxy here. And those aren't supposed to be connected or have any meaningful relationship to them. All right. So we need to go over some units of measurement and a couple of technical terms so we can understand what ARP's putting forward and how he refutes the mainstream and what the mainstream is even putting forward. So we've all heard of a light year. We're going to now bring that down to scale so we can understand what these light years are. So here's 100,000 light years. This is the length of a galaxy. If you were to traverse from one end to the other, traveling at the speed of light, it would take you 100,000 years, they say. So 1 light second, if you were starting at the sun, you would end up here. You would end up 800. I'm going to do it in kilometers because miles are gross. You would end up 300,000 kilometers away from the sun. In 1 light minute, you would be 18 million kilometers away from the sun. In 1 light hour, you would be 8 million kilometers away. In 1 light day, if you were traveling for 24 hours at the speed of light, you would be 25.9 billion kilometers away. So we've now left our solar system, left this Kuiper belt, whatever that is, and we're now 16.
The Oort cloud and the rest of the fantasy. Yes.
Oh no. The Oort cloud takes 29 days to traverse.
Oh, I sit corrected. My bad.
yeah. You thought you were Oort cloud, dude. No. That's a 29 day journey.
Year or whatever. A light month.
Yeah, 1 light month. You will be at the inner wall of the old Oort cloud. So after 1 light year, you have traveled 9.4 trillion kilometers. Unfathomable distances, guys. The nearest exoplanet is 4.25 light years away. I'm sure you guys have heard of Proxima Centauri and Proxima b. These are where these are said to be located. Aside from our star, of course, which is sub 1 parsec away. All right. Now, if you were to travel 100 light years, you would go 946 trillion kilometers. There's still more distance to be covered, though. You have to traverse the entire Milky Way, which would take you 100,000 years or 946 quadrillion miles. Were you going to say something, Stone?
I said, yeah, that's just like a factor of 1,000 from the last frame. It's just mind-splitting distances.
Dude, it gets so crazy because a light year wasn't good enough, right? They get into parsecs, which is 3.25 light years. So now we have the concept of a parsec. So you can't be writing hundreds of thousands of light years. That's too many numbers. Let's just do 10 parsecs. To round it off. So now we need to understand what a parsec is. So the parsec is defined as the, if you were to relate 1 arc second to the distance between 2 objects, the distance to create that 1 arc second of deviation between you two would be 3.26 light years or 1 parsec. So what we have here is this really easy diagram to understand this. If you were 3.2 light years away, you would see the sun and the earth 1 arc minute separated from one another. There would be 1 arc minute of angular separation between the two. So as you get further away, those 2 objects are going to get closer and closer together. This would be the distance you would have to be to put those at 1 arc minute from one another. That's how.
Just to keep that straight. Just to keep it straight, that's 1 arc second, though. Yeah.
Oh, I'm sorry, 1 arc second. Yes, thank you. Sorry, I said 1 arc minute. Yeah, dude, think about that. 1 arc second. So to get it down to 1/3600th of a degree, you have to be 3.26 light years away. That's what they want us to relate that to. Now, the second thing of importance here and is not just the parsecs and how fast light travels over time, but it's also the apparent visual magnitude and the absolute visual magnitude. So when we're looking at a stellar object, its real distance, just using mainstream, right? Assuming their distances, let's say 300 light years to this star. But when you go, so its apparent brightness is what we see it as. Let's say it's at a 3 here, so that's pretty low. Now, when they do their logarithmic expansion and comparison and their analysis for the absolute magnitude, they view this as if they could view the star from a distance of 10 parsecs away. So as if they could view it from 100,000 light years away, it would be much brighter. So the value here gets lower, and as this gets negative, that means it gets brighter. So as it gets lower, it's brighter. As it's higher, it's not as bright. So of course it works backwards, right? But anyway, Stone, if you wanted to cover the absolute and apparent magnitude scale.
Sure. The scale itself is pretty much exactly the way you just lined it out. That instead of intuitively, like we do with just about every other scale in human reality, that a bigger number would, we would guess that would be a brighter star if it's got a larger number for its magnitude. No. It's inverted, but it's not just inverted. It's a matter of a ratio. So the difference between a visual magnitude of 3 and 4 is a ratio of, would you believe, 1/5 the root of 100. Now, when I originally looked at this scale years ago, I'd never even considered such a thing. I just looked at the difference between the magnitudes themselves and came out with roughly 2.5. Apparently, it's 2.512 in terms of the ratio of brightness between those two, 1 increment apart on the brightness scale. The point that I make in the video that I produced years ago about this, to do a star magnitude, is why would they really make the scale in such a way, such a counterintuitive way? And I'm sure just by my asking the question, you guys are just, you're keying onto the answer all by yourself innately, I'm sure. It is so that you cannot form naturally an abstract mental picture between brightnesses when you look at the magnitudes themselves. You just see numbers and go, they know what they're doing. Let's move on and talk about something else now.
That's exactly what I did.
It is by design and case closed. You know what I mean? They don't want anybody taking a close look at, like you say, extragalactic, especially astronomy, and the methods that they use, the presumptions that they make. It's insane. Anyways, back to you, Alan.
No, thank you. Yeah, that scale they came up with is exactly as you said. It's designed so that you can't conceptually immediately understand what they're doing from looking on the outside in. You would have to dig deep and understand that the difference between 3 and 0.8 is insane. It's like unfathomably different in terms of brightness. So what they do is, like, we see these objects in the sky, and then we have this apparent, or we call that the apparent brightness, what we see. And then we have this other metric, this absolute metric. And we do this comparative brightness between these two to establish a distance. Now, they use the inverse square law. So to give a nice little diagram for that, the light source is a sphere. So they use a spherical distributed formula here, which we'll cover in a second, but pretty straightforward. As the light gets further away from the source, the luminosity falls off inversely.
The lightness attenuates.
Jesus, thank you. The light attenuates inversely proportional to the distance. So when we do apparent brightness, the luminosity over 4 pi times the distance squared. So that gives us this nice distribution as you get radially outward from the sphere. So at 1 astronomical unit, it's going to be half as bright, or it's going to be the it's going to be this amount of brightness, and then over 2 astronomical units, it's going to be 4 times less as bright, and then continuing on. That's how the trend works out. All right. Okay, now the next thing we need to do, now we've got luminosity relating to distances for apparent and absolute magnitudes, and then using the inverse square law. For that, there's also one additional component, and that is the spectroscopic readings, where they're shifting the light and using blue and red shifts to determine velocities. Because as I mentioned earlier, Doppler shift is a measurable phenomenon within waves, electromagnetic or mechanical, and that frequency shift, corresponds to a specific velocity. And when they look at the spectrum of starlight, they're like, oh, it's shifted from what the lab values would be in this color range. And so what they're interpreting that is a 1-to-1 velocity ratio. And then later Hubble turned that into velocity and distance. So now if you know the velocity, you know its distance and all this. So it's just more and more ways for them to come up with a way for them to determine how far away something is based off of how bright it is. And we'll see what Hubble really did to hone that in 1924 as we continue. But the important thing to note here is that a wavelength is measured right here. So if you look at the distance between these two peaks or crests in the wave, that distance is known as the wavelength, and it's measured in wavelengths. So the width of it is relative to the wavelength that you're using. And in addition to that, there's another component called the frequency. The frequency would be how many of these peaks and troughs there are in one cycle. And one cycle is considered 1 second. That is the default standard for a cycle for Hertz, for quantum mechanics, for everything. Planck's constant, for black body radiation, they're all set to a 1 second interval. So one cycle is 1 second. So how many times can this move up and down in 1 second? That determines the frequency. And as you get more of those vibrations per second, they get smaller, they get more compact. That requires more energy. As they get longer and less frequent per second, that requires less energy. So you can kind of think of it like that. If this gets scrunched together, that's the wavelengths are smaller. They're getting smaller, and the frequency is getting higher, so that they can oscillate more. So to kind of look at this, we have some ladettes holding a jump rope, and less energy equals bigger waves of the jump rope when you move it up and down for longitudinal motion there, or to create a longitudinal wave through the rope. And then if you do it faster, more energy, more excitation, you get these tighter waves and more of them. So that's the relationship there. Pretty straightforward.
Those are transverse waves, though, not longitudinal waves, just to be clear.
Thank you, sir. All right. And then we have, so when you do the slinky thing, right, that's a transverse wave, not a longitudinal?
Yeah, because the ladettes here are shaking their hand up and down. Longitudinal would be poking towards, right? Impulse.
Yeah, longitudinal. I see. Okay. All righty. So now we got our frequencies and wavelengths. And then next up, one more component. We have Lord Kelvin coming in after Newton and the lads realized that they could split light into using a prism and then categorizing the spectrum that it's made up of. Lord Kelvin got the idea to measure the spectrums. So he would split them with a light beam or with a prism, and then he would have thermometers in each individual color spectrum. And then he would, take those measurements. He would compare them to one in ambient light and then one in darkness. And he came up with the Kelvin scale for absolute zero for temperatures. So now you can relate how hot something is by how bright it is, by its color. So this is extremely important for looking at these stars. And then we go, okay, this is its apparent magnitude. Now we look at its absolute magnitude. Well, how hot would it be? Well, how hot would it? Okay, so it's this hot, okay, and it's this far, this big, this bright, so it would have to weigh this much. And it gets a little crazier because actually I think I need to skip ahead, but so I'll show it here in a minute.
Something tells me we're about to relate this to Planck and his black body radiation calculations and formulae, to wit, sigma t to the fourth comes to mind.
Ooh, we are skipping Planck, but
We're skipping Planck. Oh well,
but
that's,
that is,
I think
that
that's
is,
where we should be headed.
is directly related for the baseline of interpreting temperature for celestial bodies and all that, because that's what they use to relate to the sun and do all their backwards stuff for that. But what they do though with this is now they're starting to formulate like, okay, it would have to be this big, it would have to be burning these elements, that kind of stuff. So they start to kind of reverse what would have to transpire for it to be, you know, this bright on the scale at these distances, etc. Now, the next thing that can be done is spectroscopy, where we're looking at the starlight, splitting it through a diffraction grating, which is just like a little, think of it like a sewer grating with little fine slits. And when we split the light into that, you can look at the spectrum there. And when you look at the sun, you get a continuous spectrum. So you get no absorption lines. You get a nice smooth gradient into the other colors. And as far as I know, there's nothing that produces the entire rainbow spectrum as a continuous spectrum. I think there are some things in the lab that produce a continuous spectrum of a specific color, but nothing that shows the whole color spectrum. Is that correct, Stone?
I'm sorry, I was distracted just for a sec. Can you reiterate that?
Yeah, it was the continuous spectrum of the sun and how that's unique to the sun. Essentially, there's nothing else that has a continuous spectrum of like the full rainbow. Whereas like there's some things that you can do in the lab that will give you a continuous spectrum, but it's of a specific color.
I don't know about the full rainbow. I've done a little bit of delving into the papers about spectral analysis of the sun itself. I will concur with your initial point that, yeah, we don't see any other, quote, luminous or stellar, quote, body in the sky that has the same spectral signature as our sun. So they can't seem to find another light in the sky that actually resembles the light coming from our sun. Rather conspicuous, I must say. But yeah, that much about it. Sure.
Nice. Yeah, that's about as far as I've been able to get to it too. It seems pretty ambiguous with their like how they're not trying to like let people know. But essentially, you know, they say our sun is just it's a small star. All the other stars are like infinitely bigger. You know, we have this like mediocre baby star, right? But it's, you know, there's nothing special about it, they would tell us. But it has a unique continuous spectrum that nothing else in the sky has. So when they look out at other stars though, and things in galaxies and whatnot, they get absorption lines. And what that means is in between the light source and us, the energy emitted, you know, at that specific frequency was absorbed because it hit something that matched that same frequency. So it gets excluded from the spectral reading. And what we can do is compare what's missing from the spectrum from lab measurements and determine what elements had to have interacted with the light on the way to our eyes such that it would be canceled out like that. So what would produce that? And in the same respect, if you were to look at the emission from like a burning gas or something, instead of seeing the absorption spectrum of the missing elements, you would see those missing elements, but you would see the rest of the spectrum missing. So you would see the reverse of that if you were to look at it like that. So they've come up with this way to, now whether or not these elements exist in the way that they're telling us and whatnot, doesn't matter. The point is that they get these measurements and there's lines missing, and there's lines, these lines represent a specific element on Earth. So they relate it to, oh, there must have been that out there as well. Whether or not that's how it works, couldn't tell you. Or if that was the actual mechanism that produced it, you know, who knows? But that is what they get when they look at that. And let's see. I think that's all we need to go over for that. Oh yeah. So once they start relating like the element compounds and stuff, that's where they're like, oh, you know, the stars, this is a heavy element star, you know, and these pressures and whatnot would create this amount of element to produce this, because that's how they're always trying to backwards engineer what the star did to produce, you know, this line. Like, who knows if that's what actually is y or whatever, but this is how they build that fantasy to keep it internally consistent with the story.
They are indeed gifted at presumption.
Yes, they certainly are. And then we have Mount Wilson Observatory with Edwin Hubble in the 1920s. Now, this is where it gets really significant because he puts forward a new method of determining brightness and distance using a Cepheid variable. And what that is, that's a bright star that's pulsating. We'll skip back to this here in a second. Actually, we'll just read it now. So what Hubble did, the significance of what he did is he related velocity to distance with the redshifts. And we have this nice graph here with this nice line. And this is what he's relating here. This is a linear relationship, so a one-to-one relationship to velocity and distance as he puts it forward for what he did with his analysis on Cepheids. And what a Cepheid is, it's a star that basically glows. It has a flashing brightness to it, pulsation, and they monitor that pulsation over the course of 90 days, take the average brightness of that, and then after they have that average brightness, they then do their absolute visual, we're 10 parsecs away brightness to it. And by doing that, they say that they've like accurately determined the distance and based off of the brightness relationship because they have this pulsating star that has a specific, like a resonant beat to it so they're essentially, the way that they're looking at it is like, hey, we're not just saying like, we think this is what the brightness is. We've averaged it out over these pulsations. It doesn't exceed this amount, never goes below this amount, therefore it must be this amount. And because we know it's specifically this amount and not one of these others or in between that we would normally guess, we've narrowed down the distance to where if we got the ruler out, we could, this is what it would say. It would be this far away. So that's what they came to for their conclusion on that, and how they determined the cause of, why these stars get illuminated or get bright and pulsate like this. Oh yeah, here's the pulsation right here. So imagine watching this for 90 days.
I remember the good old days when they just called them pulsars. Back in the 90s, I actually used to drive a Nissan Pulsar right after the redesign. 1990, 91, something like that. Awesome vehicle. I was so cool back then. Anyways, back to you.
Yes. So imagine watching this for 90 days. And then after 90 days, you're like, I have the most confidence in the world to tell you the exact distance to this thing based off of its brightness. And not only that, it gets into a mass relationship too, because let me skip over to this part because this is important. It should have been ahead of it. But anyway, with this pulsation, they're like, okay, so how does this work? Well, the helium in the atmosphere of the star gets trapped due to its gravitational potential, which creates like a boundary layer of helium essentially. And that layer doesn't get fully ionized, so it can't escape. So it creates an opaque layer over the star. So as the star becomes dim, there's a buildup of ionized radiation in the atmosphere of the star. And as that builds up, it eventually bursts out, and then it gets released into a bright luminous period of the star. So that's when it's flashing the brightest. And then that buildup occurs again. It becomes opaque. And this repeats over and over again. And this is related to the surface gravity of the star. Well, they have a nice little ratio here to turn the brightness into a proportionality of density for gravitational purposes. So now you can know how much a star weighs based off of this pulsation rate, because that's going to dictate the conditions that hold the helium to it to create that opaque boundary layer that has to be overcome. So this is known as the K factor, or Eddington put some work in on it, the Eddington factor. But this is, when they talk about, this star weighs this much, well, they did that from the proportionality constant of its pulsation rate.
Oh, so that's how you weigh stars with just your eyeballs. I always wondered. I thought it was a magic trick. Turns out solid science and math.
Turns out it is. Yeah, shout out to August Ritter, who came up with that back in the day. So that's extremely important in their cosmology because now it gives them weight, distance, and recessional velocity, and then they can do all kinds of cool stuff with it. So now that we've went over what the frequency and wavelength spectrum shifts are and how they're measured through spectroscopy and how they create emission lines, absorption lines, and how they're related to distance and velocity as per the shift, we'll now look at the analyzation of the wavelength change itself. So here we have a little bit of math, nothing too fancy, but we'll read from the text here. It says the velocity is relatively easy for us to measure using the Doppler effect. An object in motion, in the case being carried by the expansion itself. Now, this is extremely important, guys, because I was making this mistake when I was going through this, and I was like, how dare you guys use V over C for the absolute velocity of a galaxy or any stellar object when you guys are, you know, when their whole belief is that there's no such thing as a V over C relationship because that would imply a preferred frame for the motion to be relative to. So everything's always viewed through the relativistic lens of the range transformations and whatnot. So anyway,
except when you got to fake those velocities, then it's right back to the V over C.
So,
is that what you're saying?
Yeah. So when I saw they were doing this, I immediately was like, I've got you. But that was my bad. The actual steelman of their position is the galaxy is not the quasar, the galaxy. That's not moving. What's happening is the space in between us and the other galaxies is expanding, and that velocity is changing the wavelength of light, and it just so happens to be carrying the galaxy with it. But the galaxy itself isn't moving at that velocity. Now, does that make any sense to anyone, or does it sound like I just came up with something to try and gaslight you all?
No, that describes the rate at which the balloon inflates that we're all on. That's the analogy. Look at that math. That's beautiful. If you don't get it, you're stupid.
It's exactly what they did, because they have all these observations, right? But then what's the redshift relative to? Well, they would need to explain that, and they would need a way to preserve the distance in between. Like, so none of that's going to work for them. And also it implies C plus or minus V, because what we're looking at here, the equation that they use is lambda minus lambda naught over lambda naught. Lambda is the measured wavelength from the starlight, so whatever it comes in at, minus lambda naught, which is lambda naught is the laboratory wavelength of that light. So they're comparing the difference, the change, and then they divide it over the wavelength to normalize it. One more time, and this reduces to being equal to V over C, which implies C plus or minus V to create that ratio, which is astounding.
There's just no getting around it. If you want to make a hard figure measurement, you got to have a frame, and that's where they lose.
That's where they lose. And then we're going to go over how they also lose in general relativity, the theory of which there is no preferred frame. But we'll see what they do to rectify that. But yeah, this is extremely significant here because this Z represents the redshift value. So the redshift value, when we see the Z and all the text and whatnot, when we're reading art books and stuff, when we're referring to redshift, the Z value is equal to V over C, or in other words, the change wavelength over the lab wavelength, which is V over C. Now, Alan, what if you're wrong about the V over C thing? What if it's what if the speed of light's constant and it's not actually plus or minus V? Well, satellites derive, or GPS rather, determines distances based off of timing intervals using the speed of light and the variance in between. When you use the range measurement equation, it essentially accounts for the Sagnac effect, which is the velocity of the receiver. So from Wikipedia here, and even I've been through it in GPS manuals where they talk about the Doppler shift being proportional to the velocity, that implies that the speed of light is not traveling at its full speed and that it's moving at its speed minus the velocity of the observer, which is not supposed to happen. But here we have the equations that they relate to it, and they're like, yeah, you got your velocity of the satellite, velocity of the observer. The frequency shift is going to be equal to the velocity of the receiver over the lambda c, which is the wavelength of which basically that just stands for the frequency that the satellite sent out. So whatever that frequency is, it's going to be V over C, which that's how they determine distances for it. It's not even just how fast something's moving. But if it wasn't C plus or minus V, it wouldn't derive the correct distance relationship. But the way that they've tried to reframe this is that the speed of light is constant, and even though there's a Doppler frequency shift, there's no change. There's no change in the speed of light itself, which is ridiculous. Because for every other wave that has a Doppler shift, you don't say that. You wouldn't say the speed of sound is constant in water. But
that is exactly what they're saying.
But when that's what they say for light.
Right.
They're like, it's just constant. That's irrespective of the motion of the receiver, which is absurd because we're looking at Doppler shift right here. When they talk about, we can't determine which frame is moved, they all look the same. If you were to drop a ball, all this stuff, guys, if there's Doppler shift, you're moving. You would be perceived as the thing moving. Like that'd be a real easy way to determine if your frame is moving. But they ignore that completely and use relativistic Doppler shift, which ends up in C plus or minus V equaling C. So that's a really cool mechanism that they employ to hide that fact. Now they're happy to use terrestrial Doppler V over C, because that's not moving at relativistic speeds. So you're not going to have link contraction and time dilation to completely remove it, I guess would be their argument. But even that's a little dicey there. All right. So now that we've got all of that relating size and distances to everything, and how much it weighs and the gravitational constants and all that, this leads us to a conclusion of like Shane just put forward earlier, that we're on this balloon and it's expanding. If you put a bunch of dots on the balloon, they all expand equidistant to one another with no specific relation to a radial center to one another.
Oh man, I smell jezzies.
Yeah, because that's the other thing, that removing the velocity from the galaxy and saying it's due to the space in between the galaxies makes it so that there's no definable central point, which is extremely important for the Big Bang cosmologists, where their interpretation of creation is that it came from nothing with no purpose or design. And in order for that to transpire, you would have to be like, well, everything's expanding out from this cosmic explosion, but there's no like definitive point from which it all started at originally. It just exploded, expanded, and at different intervals of distances and what have you. As things started to cool off, matter started to form at these different spots, and then started congealing and coalescing, or whatever matter does in space, and started making all these formations and whatnot. And the only way that you could get that is by, having this philosophy of the space in between expanding and having it not being relative to some radial center point. So they did a great job in removing all that. Now, another thing that came to the support, and so this all went down in like 1924 to early 1930s with Hubble, a guy named Friedmann, who put forward one of the first solutions to Einstein's field equations to give them a metric for which they can look at the evolution of the homogeneous universe that they talk about. We've all heard that. Well, we know that the universe is homogeneous, and all this stuff. We don't know that. That's an assumption that has to be made to solve these field equations. If you don't make that assumption using a perfect fluid to describe the energy density and mass for everything in the universe, then you can't solve this. And it has. So that's something that they bake in. They don't know that. That just is the only thing. That's the only way that they can solve this equation, is by setting those conditions in it. So the backbone of the Big Bang is based off of all of this, and it's supported by by Einstein's field equations here. So we'll do a quick breakdown, because the FLWR metric is extremely important in cosmology. This is what explains how there could be a Big Bang, and then all this matter could scatter out and then cool down and turn into quasars, galaxies, and then start making atoms and making planets and all this stuff. How did we get here? Well, we got to reverse the timeline back to the start point. And to do that, you use Einstein's field equation. So starting from right to left here, we have T mu nu, which is the tensor that describes the conservation of energy and momentum. So they put their perfect fluid medium in here. When you expand out this matrix for the tensor, this is where you set the conditions in here for your perfect medium in all directions. There's no preferred direction for the, they're creating the homogeneous thing that they say that they know exists because we solved the equation. Over here we have 8 pi times g over c to the fourth. This is basically normalizing the conservation of mass into how much curvature of space there will be, which we'll get to in a second. But you can think of this as 8 pi describes a spherical geometry in 3D space. G is the gravitational constant, so this is going to relate gravity per cubic centimeter. You can think of it like that. And then over c to the fourth makes it so that you have to have an astronomical amount of mass and energy conserved to bend space-time, because you have to overcome c to the fourth as a ratio to get the curvature here. So now, continuing on to the lambda g mu nu, we have the cosmological constant represented by lambda, which we'll cover in a second. But more importantly, we have the space-time curvature tensor here, which describes how space-time is going to curve in the presence of the matter and energy that's being conserved over here on this side. And then the capital R mu nu is a similar thing. It's the Ricci tensor, and it basically ties these all together in a way that I'm not super familiar with. But solving all of these is what creates their story. Setting the conditions to solve all these is what creates their story. Now, before we move on, I mentioned this lambda constant earlier here. So this lambda is dark energy. So this drives the expansion of the universe, because when you solve these equations, there's actually a couple possible solutions that you could do here. So you could set conditions for a closed spherical system, or you could do an open flat universe, or you could do an open expanding universe, which is the hyperbolic one down there. So if you set the conditions for expansion, this is what it would look like. And if it's expanding, you're going to need a mechanism for set expansion. So this is where they introduce lambda to stabilize it. Now, if there's no lambda, what happens is they call it the big crunch. If you've ever Googled that or heard of it, that would be when the collapse of the universe. So that's what causes that. And then due to this infinite expansion acceleration situation, this is what leads to the heat death scenario, where everything gets so far away from one another that it just basically stops vibrating and nothing exists. We go out of existence or whatever. So this the end of the cosmology that comes out of these field equations is pretty bleak, but it has a nice start to it, I guess. Okay. All right. So we went over the metrics, how to solve. And from here, we get two important factors. When after we put in all these conditions to solve these, we get two important factors. We get A dot and A double dot. A dot is the first time derivative, and double A dot is the second time derivative. So now we can describe the expansion rate in terms of a constant rate. And with the second derivative of time, we can, of that first one, we can figure out the acceleration of that. So we get the constant constant expansion and the acceleration value for the expansion. So this is where all of this comes from. And when so this is the finalized values for that when you expand out that equation and solve it all. This is what it comes down to. Now, none of that sounds particularly meaningful, and it gets even worse, because to even do this, to even get here, they had to sacrifice the meaningfulness of the T mu nu tensor, which is supposed to satisfy conservation laws. And by doing this global structure of the universe, there's no way to conserve energy and momentum to solve this. So if you guys have ever been told, oh, if you don't account for conservation laws, you're not doing anything physically meaningful. Well, that's true, and that's their standard for what they've put forward as the backbone of physics, and they violate that entirely to solve this. To even get here, they had to throw out their basic fundamental thing that tells them whether or not they're actually following, like if their math is physically meaningful or not. So threw that right out the window to solve that bad boy, to even get on, to even describe a situation where there could be an instantaneous release of energy that expands out and creates all these things as the universe evolves homogeneously. To even get there, they had to sacrifice energy and momentum conservation. So quick recap on everything. Experiments with light result in highly precise categorization of temperature and color and wavelength and frequency. Comparing light from celestial bodies to the same wavelengths and frequencies is shown to the labs produces, that's produced relative motion. So they're, taking that relationship of the change in wavelength and motion and velocity proportionality, and they're just applying it to the sky. And keep in mind, if the speed of light isn't a constant, it can't be used as a yardstick. So when we were looking earlier at the V over C relationships, like that implies that it's not a constant and nothing that there's
a little bit of a mathematical catch-22 there, I would say.
Just a little tad. So yeah, they even in their analysis, they're looking at C plus or minus V while going C is constant, and the shift that happened is due to distance expansion between us. Like that's such a perverted way to look at it when it's the natural interpretation is C plus or minus V. So to be in alignment with the cosmological principle, the velocities must be taken as an expansion of the vast distances between us and the source emitter. So the stars, the quasars, whatever they are, that's expanding between us. This implies a random distribution of masses and distances and velocities without being from anywhere specific, namely a radial center. By claiming that the velocities are not due to the sources themselves, but to the expansion of space, the radial center is removed. So there's a nice way to get around that. They relate the relationship of apparent and absolute magnitude to size, mass, distance, and age. So now you can tell how old it is by how bright it is as well. The evolutionary stages of the universe, as radiation cooled and expanded, are bound to the solution to Einstein's field equations, which are bound to the conditions which you put in to solve them. So as we went over earlier, they assumed a perfect fluid homogeneous medium to facilitate the interaction for the evolution of the galaxy. And don't you dare go thinking that fluid medium would be like physically meaningful or would serve as an actual medium. It's just an idealized medium to make everything homogeneous and evenly distribute.
Some of this is bringing to mind the art of palm reading. Are you guys getting any of that?
Yes. It's very reminiscent. Let's see. And then so more importantly is that if this redshift interpretation is off, if this relationship that Hubble came up with the pulsars and that rate of pulsation to establish an accurate distance metric, if any of that's wrong, then none of this means anything. Those distances could be anything. They could be all equidistant from one another on a sphere, on the inside of a shell. We would never know from the black and white pictures that we get. There's no way to tell. So they've constructed this entirely off of multitudes of assumptions that are now compounding that end up as a summation. The end result of what they've put forward is a way to solve field equations that violates the basic principles of physics. So not looking so hot there. So now we're going to look at some colored images of the black and whites that we looked at, that Stone was commenting on. So here's a nice false color of some galaxies. No, the important part here to look at, we have galaxies and then we have some quasars. Now, what we have connecting these galaxies is a cloud filament. This luminous filament should not be connecting to the quasars because the quasars are vast, like just insane distances away from this host galaxy, they would call it. Now, that means there can't be that means this can't span 50 quadrillions and hundreds of quadrillions of miles, right? That would just be absurd. So
through vacuum, no less.
Through a vacuum, no less. And so they come up with scenarios where they're like, oh, well, you know what? The quasar is behind it, and this is just a gas, they come up with all these different ways to try and justify it. But just looking at this image, you can't tell. But the important thing is in this spectrum, they should not be connected to one another, and yet they connected here as well. And then we go over a couple more of these instances. Here's a black and white of this one where it shows a connection. Actually, this one shows a line that goes straight through it. So they got an emission jet and and a feeding jet there that connect the two. Like none of these are showing a disconnected of the disconnectedness of what they would actually like here. All right, so in this we're looking at X-ray images of the NGC 1097 galaxy, and we see that on the faintest surfaces there are quasars here, and they shouldn't be connected with these filament. They shouldn't have these red rings around them with these that are associated with this host galaxy here. And this trend continues on. As you can see here, there's a luminous filament connected here, and then in a different spectrum, it also is also in the UV spectrum. And this is using true color. So earlier we talked about false color and true color. So this is using the dominant spectrum of light that's being shown through there. And same scenario. Oops. Same scenario. So for here, we have the old Einstein Cross, and this one is where it gets really interesting because a product of those field equations, I think it would be the Schwarzschild metric that would give the solution to this, but it would, no, sorry, it's the Kerr metric maybe? No, one of those two derives the solution for gravitational lensing. And it's said that there would be, that there could potentially be a mass that has so much gravitational potential that it creates that if there was an object behind it, it would split it in 4 ways, creating a cross around the center of the actual object that's blocking it. So how they want us to interpret this, one, is that there is a massive object right here in the center of this, at this galaxy, and in this and the mass of that is bending the light of a quasar that's behind it directly, such that we see these 4, north, south, east, west splits of it. So these are, you could think of it kind of like gravitational refraction, even though that's not the terminology they would use, but like refraction would create this sort of a splitting effect. This is what they're saying happened due to gravity. Gravity split the light in transit.
And somehow, even after bending the light that far around, what we see are still pretty much circular shaped objects. Figure that one out.
Ooh, great point. Because Harp even talks about that. So, let's see here. So when you look at this and analyze it, Harp's argument was that this galaxy can't be this massive heavy object that they're trying to assert. That this is a brown dwarf galaxy, and that this doesn't have the mass that they would need to have everything that they're saying. And if it did, it would, because the mass and brightness ratio, right? Because it's how he's determining the weight of this galaxy is by its luminosity. So when he looks at this and he sees that it's not bright enough to have that much mass, you can calculate how much or how bright it would have to be to have that amount of mass, and it would be a magnitude of -25. Which is it would be the brightest object in the sky.
-25?
Yes.
Wow.
There's quasars that are -23, and this would be brighter than them. So, and that's not the case. So that's not what's happening here. But to keep this illusion alive, they just have to say that this has that amount of mass, and then when you calculate that mass to produce this effect, well, this has to be like the densest object in the universe, because nothing like to create, like when we looked over this, this 8 pi g over times g over c to the 4th to create this amount of bendy light for them. There's nothing that weighs this much in the known universe except for this to create this for them, even though it's not as bright as they need to be to have that mass and to begin with. So just like take that into consideration. And also, as Stone was saying, that these aren't very elliptical. And in that, there should be there should be an additional effect due to relativity where these are way more elliptical, and they're not. So the presence of gravitation and the way that they would like us to think about it in terms of space-time curvature, due to the conservation of mass and energy into a gravitational field, to curve space-time is not a realistic thing. Has nothing to do with it. Although they did find a nice object in the sky that has a configuration that could be construed as an Einstein Cross, but it actually has nothing to do with it. And also, you can see that there's filaments connecting everything in here. So that's not supposed to happen. Now here's another image of the old Einstein Cross there. So this is
can you zoom in a bit on that frame?
Negative, Ghost Rider.
Not worried.
Yeah. And then here's just some more images to close on here, just going through more objects in the sky, more eye candy. Now this one's done in black and white, so no eye candy here. But here we have color. The candy's back. This looks very cool. So here we have a jet stream emitted from a galaxy. We have a quasar at the end of said jet stream. Or no, I'm sorry. This is the end of the jet stream. We have a quasar here at the end of it, which definitely didn't get ejected from the center of the galaxy. Now, whether or not these things got ejected and all that, because ARP's whole position was that the quasars were being misinterpreted because they would have to come first in their cosmology because they're further away based on their redshift. So ARP was saying that they're misinterpreting redshift completely, and that redshift is an intrinsic property of matter creation, and that these galaxies are creating matter, and as they're churning out this matter, it goes through a period of when it's like the most active and energetic, and then it starts to mature and die down, and that's when its redshift changes, and that recessional velocity that we're getting starts to become a lower value. Now, to my knowledge, nobody has measured like what was the redshift this year, what was it the next year. It seems to be all the same values constantly. So I wouldn't necessarily hinge my hat on maturing of things and all that to like rewind it. But that's what he was putting forward, is that the center of the galaxy is ejecting a jet stream of matter, and then that matter clumps together, becomes its own system, and then it will eventually become a companion galaxy to the one it was born from. That's what he was putting forward with his cosmology, and none of it could be refuted because he was using the same observations that they were using, just interpreting the shift differently in terms of causal mechanism. Because what he was finding with these filaments being connected is that they can't possibly be these astronomical distances apart because they're physically connected. It doesn't make sense that they're connected for quadrillions of miles in separation. The only way that they could be connected is if they were close together, and the redshift didn't have anything to do with a recessional velocity 1-to-1 and the way that they attribute it. So here's some more cool pictures of jet streams ejecting things from the centers of galaxies, and then we have bright objects next to them, which are quasars. Now, the big point of contention here is this right here, where there's a galaxy that has a starburst cone. So we have a more active cone of energy here. So if you were looking at this in terms of spectrum, you would see a lot of radiation activity coming from this direction going outwards. And then they have an input stream they're calling a cold stream, which is where matter is going into the galaxy disk, and then it's getting churned in there, whatever black hole stuff is going on, and then boom, it's getting shot out after it's been compressed, and all that is what they would like us to believe. And in this jet stream here, there are two quasars in it. Now, ARP would say that the quasar came from the center of the galaxy, and it's ejected out with the stream, and it's just basking in the glory of said stream, accumulating, the matter that's being ejected out, and then eventually that quasar will, adopt that matter and whatever it does, and start creating stars and become its own little companion galaxy to the host galaxy that it created. And the mainstream cosmologists say, nope, that's not what's happening. The quasars are behind it. And the only way that they could make that assumption is by assuming how much hydrogen there is exactly in the beaming angle at which the star is hitting that hydrogen, and that's not they don't have measurements of those. They have to assume those things to even, they have to further assume those to rule out ARP's explanation for it, which if you're just ad hoc assuming more things to say no, then like that's not really refuting it because you don't have an actual measurement to back up your assumption there. So that's the only thing that's put forward. Like that's how these guys battle. They're locked in a stalemate. No position can go anywhere. So if someone starts to deviate, the only way to show that they're wrong is to just silence them. And that's what happened with ARP, having his ability to view the sky stripped from
you gotta shut her down.
Got to take her down. You got to take her out back and put her down or whatever. Now to close this off here, shout out to ARP, peace be upon him. But to close this out here, we are going to read a little bit from YP Varshini. I don't know. This guy, go ahead. What is it, Stone? Tell what is his name?
I wanted to say that his name was Varshini.
Varshini, thank you. YP Varshini. So this guy says the redshift hypothesis for quasars. Is the Earth the center of the universe? Really interesting paper from the 1980s. It was. So the abstract here is it is shown that the cosmological interpretation of the redshift spectra of quasars leads to yet another paradoxical result, namely that the Earth is the center of the universe. Consequently, or consequences of this are examined. Now, to give a TLDR of this paper here, there are 57 quasars that are surrounding the Earth that allow that are such that if we were in a different location, we wouldn't see all 57 of them. So he makes the argument that we are in a unique position to view all 57 as if they are fixed to outer shells, that are radially outward from the Earth, putting us at the center. Otherwise, we wouldn't see all 57. So that's the base of his argument here. So he goes over the data and the redshift values for said 57 quasars, and we'll get to the end here, how he tries to rectify this, as he said he was going to go over the consequences are examined. So he says, in other words, the cosmological redshift hypothesis that the quasars in the 57 groups in table 1 are arranged on 57 spherical shells with Earth at the center. This is an extraordinary result. Some of the possibilities we shall now consider to accommodate this result may be disturbing, but we must consider them possibilities dispassionately. So that's a really interesting
cough, Hubble cough.
Dude, he's like, guys, nobody wants to hear what I'm about to say, but we all are scientists and unbiased, right? We should consider these dispassionately and just see what happens. Well, what blasphemy is he about to propose here? Well, number one, coincidence in distance could be that could be possible if there was clustering. However, examination of the coordinates of various members of individual groups showed that in most cases there is no such correlation. Hence, this explanation has to be ruled out. All right, so observation doesn't fit the hypothesis. So we ruled that one out. So it's not clustering. That's not a coincidental clustering. Okay. Hypothesis number 2. Quasars may be arranged like atoms in a crystal lattice, with the Earth being at either end of the empty lattice site or at a suitable interstitial site. Should that be the case, one would expect some pattern of regularity in the directions of the quasar belonging to a certain group. No evidence is found, and this possibility must also be abandoned. All right, we're 2 for 2. Not looking good. So no crystal lattice structure of coincidence, because what would happen is in one direction there would be more quasars on one side, and that doesn't really seem to be the case. Let's take a look at number 3. The Earth is indeed the center of the universe, and the arrangement on the quasars on certain spherical shells is only with respect to the Earth. These shells would disappear if viewed from another galaxy or quasar. This means that the cosmological principle would have to go. It also implies that a coordinate fixed to the Earth would be the preferred frame in the universe. Consequently, both special and general theories of relativity must be abandoned for cosmological purposes.
No,
the absolute whore!
You can't do that. You can't do that, buddy.
That's illegal. You can't do that. He also list another issue. We must also consider two other possibilities which have been discussed in the literature to explain the apparent redshift of quasars. The difficulties in assuming that the redshifts are gravitational are well known, and we need not repeat them here. Let's see. In addition, there is also a reason why there should be coincidences in the mass to
radius.
Is it radius? Because like they need
as in the spherical radial distance calculation, that kind of radius.
They say as their mass to radius relationship, essentially a function of their mass to radius for the gravitational redshift, right? Because that goes in tandem with like the angular size of the star. So like, dude, they're so backwards on that too when they get into deriving gravitational redshift, because it's based off of a radius that's based off of a point source of light. So they literally they're like, this is the radius based off of its brightness, essentially. So the local Doppler interpretation of the shift has serious difficulties. In addition, it will have to explain why the quasars are ejected in spherical shells that make concentric circles around the Earth, which is, untenable for them. They invented the cosmological principle to avoid that. We are essentially left with the only possibility, which is number 3 in the cosmological redshift. Oh no! So we must abandon all these things to interpret. However, before we accept such an unaesthetic possibility, we must raise the question: are redshifts even real, bro? We wish to point out we have posed an alternative explanation for the spectra of quasars. Yeah, ARP also posed an alternative explanation, and he lost his ability to view objects through a scope in America. So hopefully this guy fared a little better.
Somebody outlaw that guy from telescopes. He's no longer allowed. Obviously, he's got dangerous misconceptions and misinformation about what he's looking at, so he can't be allowed to see.
You can't play with our toys anymore.
Absolutely insane, dude. And so, yeah, that is the end of the Prezi. So I have a quick conclusion recap here. So I'll read it out here. Modern cosmology is built on a house of cards. The assumptions made to satisfy judging distances for celestial bodies is rooted in circular reasoning, which in turn gets reified by mathematics that have to violate conservation laws to even give the appearance to be tenable. In any other scenario, something like that would never be permitted. The speed of light is terrestrially measured as c plus or minus v relative to the latitude, and also relative to the observer's velocity in other scenarios where light is being measured, which means it can't be used as a cosmological yardstick which is the backbone for deriving physical meaningfulness out of the cosmos for them. Because without a constant to use, they have nothing to make it relative to or to use as a, how fast does light travel in a year? Well, it has to travel at the same speed forever. Otherwise, there's no unit of distance created from that for them. Otherwise, the distance would be unreliable. Terrestrially, the relationship between velocity and distance holds with Sagnac and Wang. So if you do interferometric measurements or Doppler measurements, you will terrestrially measure a proportional relationship to wavelengths and velocity. Absolutely. However, to explain interferometric readings, no one has ever proposed that the space in between the source and the emitter detector that the source emitter and the detector is expanding in all directions to create a frequency and wavelength proportional to the velocity of the expanding space between them. And if they did do that to explain like a Sagnac apparatus or something, the light would combine after completing the expanded distance, and there would still be no phase shift. There would be no actual displacement. So like what they're proposing is, it's not even physically possible for it to have the shift and then still be the same speed for the observer. Like you don't measure it that way. It's absurd to suggest that the space, but yeah, I read that one already. All right. Additionally, ARP made a number of observations and wrote a number of papers to get his ideas out there and explain these. And he got refereed every time, meaning that instead of being able to publish his his document. It got called into question. He had to defend it. And then the person, which is fine, like, that's not to be unexpected, I guess, but happened every single time. And every time it was refereed, it was denied because he couldn't possibly be right. Relativity has to, like literally the arguments that he was getting were just, you think you're smarter than Einstein type stuff, just nonsense. Like, bro, the galaxy isn't bright enough to have that much mass. Like, how are you going to tell me that's gravitational lensing? So ARP had the mathematical ability to like refute this and the credentials to, back it up. So they had to shut this guy down hard because like some guy posting his thoughts about this on Vixra is not going to get the same amount of traction as if this gets published in like a mainstream journal, like if this came out in Nature, everyone would have to take it seriously. And we saw the same kind of protection and censorship going on when Hilbert Dingle tried to publish against relativity regarding the twin paradox. He couldn't get it published. And, despite the fact that nobody who believed in the theory could answer the paradox, they would not allow him to publicly put it out there in a prestigious journal of Nature magazine. Couldn't do it. All right, so accepting intrinsic redshifts into the picture, meaning that the redshift value isn't due to cosmological velocities or distance expansion, opens it to many possibilities. Earlier in the chat, I saw Cami mention that redshifts can be created from relative motion through a magnetic field, and that's absolutely true. There's something called the Stark and the Zeeman effect. They're magnetic and electric field line splittings, respectively. So basically, if you send electromagnetic radiation through a magnetic or an electric field, that can cause shifting in it. It's known as the Stark and Zeeman effects. Those are well-known effects. I used to have a video from it's that guy's name, Apotheosis Theoria, who had a cool video on what's that called? He had a ferrocell, and he was moving the ferrocell over a stationary magnet. And in the color spectrum of the light produced from the ferrocell, you could see that one end of the pole was a little blue, and then the other end was a little red. You could literally see the shift in the light as it got retarded moving through the field, or as it got boosted moving through it.
Yeah, that would be Ken Wheeler, indeed.
Ken Wheeler, yes, thank you, sir. Thank you, sir. So yeah, let me move us back to the panel here. Stop sharing. All right, we're back.
Nice. I like when they cannibalize their own when they put out something that we would agree with. They're like, dude, you know what? He can't be allowed to speak. Actually, that's what we got to do.
Dude, they would referee him and be like, nah, this doesn't exist. And then a couple years later, somebody would come through the exact same data and be like, yo, relativity explains this with gravitational hoobly-doo. And they're like, approved.
Yeah.
Stupid.
The gravitational hoobly-doo? That's my favorite. He's in. Yeah. Get him in here.
Oh, you solved it with this metric that requires you to abandon conservation? Sweet, dude. Signed and approved.
And now they're like, how come you don't have any peer-reviewed papers that say all the other papers are dog shit? It's like, well.
It's not Galilean. You're in.
Yeah, pretty much, man. Pretty much. And then so check this out. When I was looking at the how they derive the FLW metric, what they do now is they use the CMB, the cosmic microwave background radiation, as a preferred frame to make the velocities relative to that, even though they're double extra not supposed to do that, because they're doing it strictly as a mathematical frame of convenience. Dude, no, you're not allowed. You can't do that. If you can't do it from a different frame, it's not equivalent. Doing it from one frame that's mandatory and then saying that it's done out of convenience and they're all equivalent that's not how that works. That's not what that means. But that is the backbone of what they do. So
everything's relative except the lab frame is the end result. There you go.
Pretty much. Pretty much. Are there any questions from you lads or any comments? Any additionals?
What does Einstein's cross prove again?
Ooh, great question.
Right.
It proves it.
Celestial refraction around another quasi-stellar body. That's what that does.
Essentially. So for them, they have a formula where it's like the mass of the gravitational potential over the radius, all this stuff, and what it gives for them is like one, that they're correct about the mass of what they're talking about, and then two, that it could only be explained as a function of conserving said mass into a gravitational field to bend spacetime, which is different from the Newtonian concept of how light would be affected, because anyway, it's a whole thing with the was the star thing that Eddington did. But basically, using that geometry, it basically makes it mutually exclusive to relativity, because of, only this much mass would create this much bending, and yada yada. So it just reifies
For clarity, that's Eddington talking about light being bent around the sun, which you can only observe during an eclipse.
Yes, that one. That exact scenario. So that formula is contingent on mass and radius. Those are the only two variables in that formula that change, and the mass cancels out. So that's not, not relevant. And then then it becomes about the radius specifically, because the influence of gravitational potential is going to be viewed like radially outward from that point. So if you took the distance from the center to the limb of whatever you're talking about, in this case, it would be like the sun, that length and distance radially outward from the surface is what they measure the strength of the effect of the gravitational field in. So you're going to get this much amount of arc second or arc minute displacement if you're this far away from the radial center of it. So like I was saying earlier, it gives them like, okay, the star is this angular size, but like, what's its radius for real? Doesn't matter. It's whatever the computation gives that gives us the correct answer. That's what the radius would have to be, because that's the only variable that changes, and it's the only one that has like the impact on it. So it's just whatever it has to be.
Yeah, shout out to Gleam in the audience there. He's in the chat right now talking about the shenanigans committed by Chandrasekhar, among others, I imagine. Hey, G, what's up, man?
Always shouting out Gleam.
Shout out to Gleam. Yeah, I think I think he did say that. I can't understand it, and so no one will. Ban him. I think that was a quote from him. Actually, funny you mentioned Chandrasekhar, because ARP met up with him, and oh man, I wish I had the quote for it. They had a dinner, and like ARP said something legendary to him. But yeah, that guy didn't like ARP. He didn't. Anyone that was against the mainstream cosmology, was the bad man. All right. So let's see. Looks like we're good on questions, comments. I see. All right, well, we will go ahead and wrap up, lads.
Excellent, Prez, dude. I can't believe you threw that together in like 2 days.
Yeah, pretty straight up, man. Cool.
Thank you. It was fun to go through it all and recap it, and like going through the math of what they're of how they derive the shifts and all that was hilarious. Just seeing the V over C, and then the one formula is literally just, it's essentially the Sagnac formula, but with no length, because they'll just derive the length based off of the distance off of that anyway.
Like,
so
literally mathematical 3-card Monty. They were like, dun, 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 where is it?
And
Where's the C plus V? Oh, it's still here. I'm just kidding. It's been here the whole time.
One formula, we shall bind them.
One formula to rule them. Dude, that's
built a cosmological house of cards. I think you summed it up pretty well. Like one giant leap of assumptions based on other giant assumptions, and then we have at the end a giant assumption candelabra that'll just completely fall apart with like, wait, how far does it really go? Wait, is Redshift real? Uh-oh. Poof.
Is Redshift even real? Like, dude, that dude's hilarious. He was like, guys, I can fix this. Is Redshift even real? Oh man, hilarious.
Nice.
All right,
Yeah.
lads. We will see you guys next Sunday. And then our schedule for the week will be Celestial Theodolite at 8 p.m. Eastern. So check us out there. That'll be on Earth Awakenings. If you want to learn about the old Celestia Theodi, head over there.
Tomorrow night, just to complete that coordinate.
Yes, sir. And then Tuesday, not to be confused with Monday, will be Ether Roundtable number 102, where we'll have a special guest presenter, Paul from the channel Plain Reality / Twitter account, Paul Plain Reality. He's going to be doing an awesome presentation on terrestrial refraction and all that goes into that. And then Friday will be Twitter Community Night. We've been we talk about Twitter Community Night, but we have not been live for Twitter Community Night in a couple of weeks. We've been busy doing prezzies and using Friday night as the night to do all the back end research for the presentations on Sunday and such. So there may be a Twitter Community Night for us, but if not, the boys will definitely be holding it down. So if you want to stay tapped in with them, just head on over to Twitter. There will be a space every Friday. And then we'll be back again on Sunday, which I think it's Shane's turn to present.
Yep, you're on deck, man.
All right, we'll find something.
Nice. Oh, I heard he's going to give us a damning presentation.
That was bad, and you should feel bad.
Well, you know what they say. That's just water under the dam.
Wow. I can't. You should. Jeez. I feel bad for everyone watching and you at the same time.
All right. Well, stay tuned for Sunday. It'll be a special presentation on the history not related to dams.
Nice.
But it will be very damning.